So true breeding is when you have two homozygous alleles or genomes that will be represented in the offspring, which will have the same phenotype or characteristics expressed from the parents. So say here you have two dominant A's and then two recessive A's, that's the mother and the father, and so the homozygous is always going to express whatever characteristic it has. So say the two big A's is going to be blue eyes, and then the two little A's are going to be brown eyes. The child, or the offspring, is always going to have either the brown eyes or the blue eyes. However, if you have a heterozygous, so you have a dominant allele and then a recessive allele, this is possible as a carrier. So this won't actually be expressed in the parent, it has to be the same expressive. So while it's still like blue eyes, it might be a carrier of brown eyes. So you could have two blue-eyed parents, but carriers of brown eyes, and then that could make a brown-eyed child, and it wouldn't be a monohybrid cross of true breeding, because it wouldn't be the same characteristic expressed as the parents. And then we have codominance, which is when you have two different alleles that occur for the same gene, but both equally dominant. This allows the phenotypes both to be expressed in an organism. So you could have, an example of this is snapdragon flowers. That's a bad drawing of a flower. So a snapdragon flower is an example of codominance. So it's codominance. So snapdragon flowers can have multiple alleles, but an organism can only carry two versions of the allele, one on each homologous pair. So a red flower allele codes for the production of an enzyme, which catalyses the production of a pigment. So another example would be blood groups. So you have blood group A, which has antigen A in it, and then blood group B obviously has antigen B in it, and as blood group 0 has, or O, has no antigens, so it's blood group O, which is, you have a little I whenever you do blood groups, IA and IB. IO has no antigens, so it's both recessive to blood group A and blood group B. So this is the immunoglobulin gene that's produced for antigens. For example, blood group A could be, so if you had blood group A, you could have IA and then IO, because this one is recessive to the A. And so if you're blood group O, you have to have two recessive homozygous genes. But you can have codominant, so you could have A and B, which are equally dominant, so you have both antigen A and antigen B in your blood. Determining the sex of a person, humans have 23 chromosomes. So 22 of these chromosomes are exactly the same, but on the 23rd pair of chromosomes, the 23rd pair, the Y is a lot shorter than the X. So I have a picture here. So as you can see, this is the this is the X chromosome, which is females, and this is Y chromosome. As you can see here, it's a lot shorter than the Y chromosome. Yeah, so I'll get to that in a bit later. So you have, I'll just put that to one corner. So you have, if I just do a little diagram. So you have, just if you remember how we need the parental phenotypes, which is male and then female. That's the phenotypes. Then the genotypes for a male is X and Y, as you can see on the picture, X and Y. And then the female is X and X. So the gametes are X, Y, and X, and X. And this is F1 because this is the first offspring. these should actually be circled. So those are the gametes coming from the parents. There we go. So if you put that into a little Punnett square, you can see that you can get half and half. Half of the offspring is female, half of the offspring is male. And then X, Y. So that'd be XX, and the XX, as we can see, is female. XY is male. XX is female, and then XY is male. So you would say 50% is X of offspring is XX, and 50% of offspring is XY, which would mean a half of the offspring is male, and then a half is female. So you would explain the genotype and phenotype in the sentence after you've done your diagram. This is sex linkage. This is a type of inheritance that is on the 23rd chromosome, which is anything that's inherited by the 23rd pair of sex chromosomes. So anything to do with female-male chromosomes. Generally, you have a X, and then you have, say, A as the allele, because it's on the chromosome of the X allele of the X chromosome. Does that make sense? So yeah, so whenever you're doing inheritance from a male or female perspective, that's called sex linkage, which is a type of inheritance, and you always write it with whatever chromosome you're on. That was supposed to be a B. Right. So any recessive, so females have 2 X chromosomes and males have only X and Y. As you see on the picture here, the Y chromosome is a lot shorter than the X chromosome. So the X chromosome has a number of genes that the Y may not have, because there's all the space there that the X gene may not have. Any recessive allele on the X chromosome, so this is the Y chromosome, and this is the X chromosome. So female and male. Males is the shorter one. So any recessive allele that may be on the female, so this is the recessive allele on the locus of the female, is going to be expressed because the male chromosome is not long enough, and it won't have a matching allele to dominate it or to even suppress it. So this recessive gene is always going to be expressed, or very likely to be expressed, because it doesn't match up with the loci on the Y genes. So there's no other dominant allele to overall the characteristic or the disease. So an example of sex linkage in a genetic condition is red-green colour blindness. That's actually the wrong colour. But we have, so this is sex linkage disease. That's red-green colour blindness is an example. Haemophiliacs, or haemophilia, is another example of the sex-linked genetic disorder. The blood clots too slowly in the absence of a protein clotting factor, and this obviously bleeding can be fatal. So if a male inherits the recessive allele on the X chromosome, there's no corresponding dominant allele, so it will develop the condition. Any sex-linked diagrams will always have the chromosome first before the allele, so that's what I was talking about. So when you have a sex-linked diagram, the chromosome always comes first. So if it's on the X and you had you're a haemophiliac carrier, you would have, say, the allele for haemophiliac is a little b, you'd have X then a little b. You wouldn't just have the b like you normally would. So, yeah. Sometimes with the Y chromosome though, because with this space here, there's not actually always a matching allele. So if you did have the haemophiliac allele on the female, you wouldn't, and you wanted to see the cross with the male, you would just have a normal Y, as the Y wouldn't have a corresponding allele, so there'll be nothing there. So yeah.